Hi, my name is Yuriko. I'm from PSC. I've been working on this DKFHE project with Enrico this past few months. And within the project, we implemented BFV scheme first in Python. So today I'll be explaining the math behind BFV scheme. Yeah, my talk will be a little bit different from, all the other application talks, but hopefully you guys like it. So since my talk is only 15 minutes, so my goal here today is to give an intuition of how you can construct one FHE scheme from this mathematical problem called LWE. So yeah, here we go. So how many of you here have heard this word, learning with error? Oh, okay, that's quite more than I thought. And how many of you guys here have solved a linear equation with, let's say, like 2 or 3 variables like this? Definitely more than a number of people who have heard LWE, I assume, because you learned this in middle school or high school. And if you know this, you're good to go. You will perfectly understand my presentation today. So imagine solving a set of linear equations for the variable a, b, c that are all integers. So let's say something like this. And as you all know, solving this is pretty easy. You can use Gaussian elimination, or you can just try hard to solve them all. And now imagine our new goal is to make this hard. So here's my attempt 1. How about taking mod q, meaning that do all these operations over the finite field modulo q. So I just added all these mod q at the end of the equations, but it turns out that no, this is still easy because Gaussian elimination still works as well on finite fields. So this is not good. So here's my attempt 2. How about adding some randomly sampled noise constants? E dash, E dash dash, E dash dash dash, constants to the equations. This is actually still possible to solve all these unknown variables using linear regression. It's just an ML technique. So this is not good yet. So here's my attempt 3. How about combining attempt 1 and 3 at the same time? So adding some noise constants E, these, and operate over finite field modulo q at the same time. So it turns out that this set of noisy modular equations are really hard to solve. So when you find some mathematical problem that's really hard to solve, we can always build, not always, but we can try to build some cryptography out of it. So let's construct a private key encryption scheme using this. Oh, I forgot to mention, but my talk will go like this. So we will construct private key encryption scheme first, then we will expand this private key encryption scheme to public key encryption scheme later. So here is how we can construct private key encryption scheme from LWE problem. So LWE is defined this way. It's a multiplication of A times S, where A is defined as M by N matrix, and S is an N column vector. And adding E, which is M column vector, to them, you will get B, which is an M column vector. And you might think this is like some complicated thing, but it's just same as this kind of linear equation with matrix in it. So if you can see with concrete values here, if you take a look at the first row, it's just that 3 times 2 plus 4 times 1 and plus 2 and 3. And you will get, plus 3, and you will get 13 on the first row. So this is just, as you can see, same as this kind of linear equation. And as we learned from here, noisy modular equations are really hard to solve. This S value is really hard to solve, given that these are randomly sampled error values. So people can sense that this can be a secret key and we can encrypt something. So this is how we go. Let's skip about parameters to be more secure. We will talk about this more in depth in the workshop that starts at 1:30. So if you're curious, come by. So now we can encrypt some message using this secret key. So let's represent message M as a vector with M elements that are all in the finite field modulo Q. So to encrypt message M, we set AS times A times S plus E plus this message vector, and that will be equal to B. So remember S is a secret key, and now we can define the ciphertext C as a tuple of two elements, which is B and minus A. So this is a diagram to show this encryption scheme, but it's just same as this before, and now only difference is that we have this message column vector. So yeah, this is the definition of secret key encryption scheme. But given S, here's the catch. Can you decrypt ciphertext back to M0? This is original message. The answer is no, because of this E, which is randomly sampled noise. So what do I mean by that? Here's the reason. So let's see together. To decrypt C, which is a ciphertext, defined as B and minus A, given secret key S, we can try to calculate M back doing B minus A times A, B minus A times A. But we will still get this back. But this is still noisy. And you have to note that the decryptor doesn't know what E is because this is randomly sampled. So this is still a noisy plaintext message. So in order to get the original message M0 back, we need to have some way to store them, the message and error value, separately. So this is how we do. Imagine this is a ciphertext bit, and our goal is to store message M and the error value in like a separate place. So how do we do that mathematically? This is how we do. And how about scaling M0 by some factor up, and then bring this message up to most significant bit before adding to the AS and AS plus E. So the M0 is in the higher bits now, and it doesn't get jumped up with the error bits at the end, at the least significant bit. And when you want to decrypt the noisy text message, noisy plain text, we can scale this noisy plain text M dash by the inverse of the factor we used, then chop off the least significant bit, which is only error value, to extract this M0 back. So this delta is the factor that we use to scale up and scale down, taking inverse of it. So I have like a concrete value to show how you scale. So I just used a value 10. Note that this is not a modular arithmetic for simplicity for now, but if you can, if you see the second row, instead of adding 1, which is the original message, 1, I scaled it up by multiplying by 10. So now you have 10 here, so 19 is the value here. So after you extract this part, which is 5, you get 14. And now you have to do 14 times the inverse of 10, so 1 over 10. Then you get 1.4. Then this is I'm just giving you intuition, but you just have to chop off the least significant bit. Now you get the original message back successfully. Okay. So let's recap what we've done. So we've constructed private key BFB scheme now. Now our last task is to extend this to public key BFB. To me personally, this was the most confusing part when I was reading the paper. So let's go together. So recall the ciphertext is defined tuple of two elements B and minus A with a secret key S, which is sampled from some distribution. So it's defined this way. We've already seen this. But you might notice that this is not perfectly secure, because if you change the message value M, adversary can see that the first component of the tuple CT changes with the second component of the ciphertext unchanged. So indistinguishable property doesn't hold with this. This is like a very academic notation to say that given two different ciphertexts, you can get some sort of information about plain text just by looking at two different ciphertext messages, which is not good. So our new goal here is to switch this secret key S to public key, which is defined by PK0 and PK1. So this is the definition of public key. It's just AS plus E minus A, which is a zero encryption under secret key S. Maybe I can zoom up a little bit. Yeah. This is like a fancy term to say that you just have to plug in 0 into the message variable, then you will get this. And now, how do you encrypt using this public key? You can encrypt your message with an ephemeral key U. This is also another fancy term, meaning that temporary key. Yeah, ephemeral means temporary, which is just a random value sampled from uniform ternary distribution, meaning that it's either -1, 0, or 1. And you also need to sample these error values from some discrete Gaussian distribution. Yeah. And how do we encrypt it? So ciphertext is defined as, again, tuple of two elements, which are this value and this value. And then you might be thinking, like, why? What are these variable means? Like, why do you do this? But important point here is that this is just a nested two LWE samples. What do I mean by nested? Okay, let me zoom in a little bit. So this PK0 part is defined AS plus E. This is one sample of LWE. And then if you take an outer whole first component, this is in the form of U times PK plus E plus M. This is also another LWE sample. If you take a look at this, it's the same form in the first component here. So U is A, PK is S, and we just have to add E and M. This is the first component here. So as I mentioned here, forget about delta for now. This is just some factor that we use to scale the message up to most significant bit and scale it down by taking the inverse later, as I just explained before. So now, okay, we have achieved this indistinguishable property. Sorry, I can never pronounce this word. So now, because every time you encrypt a message, you sample, you sample a random value U and E, so you would never know which PK you used. So let me finish my presentation really quickly by explaining how you can decrypt this. So decryption works as the following. It's defined this way, and you might be thinking why, but it turns out that you can nicely cross off cancel these terms, and then what you have left is the message with some new error. So now you just have to do the scaling down part that I just explained, multiplying the inverse. Then you will get the original message back as long as this error value is within this bit. So yeah, this was my attempt to explain math behind BFV within 15 minutes. So yeah, so this is our implementation of BFV in Python. So if you're curious, you can take a look at the code. Maybe it'll make more sense to you rather than listening to my explanation.